Good morning, one and all. So let us start today's class. So in the last class, we have discussed about learning the parameters, that is w comma b. So we have seen two methods, that is guesswork, and the next one is error surface. So both are not feasible. This is not the principled way of learning the weights or parameters w comma b, because in the sigmoid neuron we should learn these parameters to minimize the loss function. Okay, so now we will discuss what is the principled way of learning these parameters w and b. Now before that, let us see what is a gradient. You might have studied this gradient in your previous courses. So grade means it is a slope in a particular direction at a specific point. So gradient means a slope of a curve at a given point in a specific direction. How to find a gradient of a function? Suppose we have a function of n variables. Suppose f of x1, x2, so on, xn. How to find the gradient of this function? So gradient is denoted by this f. This is the gradient notation. It is called nabla. Now what is the formula thus? We should take the partial derivative with respect to all the variables. Here we have n variables, x1 to xn. So you write in a matrix form dou f by dou x1, so on, dou f by dou xn. Okay. In the problem, if they are given at point P, okay, suppose, so then we should take at point P, you substitute the point in the derivative. This is the gradient. So this is the gradient formula for n-dimensional function and at a given point P. Okay. Now we should know the difference between a derivative, a partial derivative, and a gradient. Suppose let us take the last function is only a function of w, that is w square. You know already, if I say what is a L dash w, that is derivative, that is 2w. Okay. Suppose second case, suppose L of w comma b equal to w square plus b square. Now here we have two parameters. Suppose L of w equal to w square plus b square. Then what is the partial derivative with respect to w? What is that? In that case, when you do a partial derivative with respect to w, b becomes constant, so it is 2w. If I do reverse, if I want to find out the partial derivative with respect to b, that is obviously 2b. Okay. Now what is a gradient? It is a partial derivative of all the parameters, all the variables. Now since we have two variables here, now the partial variable will become what is del of L of w comma b, that is partial derivative of L with respect to w and with respect to b, isn't it? Now what would be the answer? Suppose let us take this example. It is a function of two variables x and y, 0.5 x square plus y square. Suppose, for example, the function is of two-dimensional with two variables, that is x comma y, 0.5 x square plus y square. Now find out the gradient of f obviously what is the partial derivative of this function with respect to x? That is x. Is it okay? So actually 0.1 into 2 into x. So x with respect to y, to y. But if they are asking at a particular point, that is 10 comma 10. So what is that now? At particular point P, which is of 10 comma 10, then the answer would be 10 means x is 10, y is 10. 10 into 10 comma 20. Okay. Now that is about a gradient. Now, so we will discuss an algorithm that is called gradient descent algorithm. What is that? Gradient descent algorithm. In the short form we call GD. Okay. So we use this to learn the parameters. Learn the parameters. What parameters in our sigmoid neuron? W comma B. What is B? B is a bias. What is W? It is a weight of the input. What is input? X. Now, so here, so vectors of parameters say randomly initialized. We want to learn these parameters. I am writing in a vector form or an array form. That is theta. Now, you don't confuse. Theta is a vector containing two parameters W comma B. Is it okay? Now, before that, what is the gradient descent? It is the iterative. Obviously, we'll go with the cycles or iterations. A first order optimization algorithm used to minimize the loss function. It is widely used in DL and ML. Okay. What is the goal of this algorithm? It finds a better way of traversing the error surface so that we can reach the minimum error. So let me go back to the surface. Here we were traversing the error surface which is of in the flying blanket shape. We are traversing like this. Okay. Now we will find a better way of moving around the error surface. What is the goal? Obviously goal should be reaching the minimum error point. Where is that? It is a dark blue region. Okay. So we find a better way or a principled way of moving in this surface so that we will come to the dark blue region which is indicating a minimum or zero error. Okay. Now we did not move in a principled way. We are moving randomly. Okay. In the previous two techniques of guesswork and all those things, we are not moving in a principled way. There is no logic behind it. Now we have to move logically so that we reach the minimum error point. Now, so obviously, so let us discuss what is the best way or what is the proper way of moving in the error surface or traversing in the error surface. So this is theta. Now we have written in the form of vectors. I mean these things. Okay, let me go back here. Yeah. So this is delta theta. So we are defining a delta theta, that is a changes in the two parameters. Why? Because so initially we go with the random values. Suppose in the previous example we started with, I don't remember exactly, maybe the 0.5 comma 0.2. It may be right, I guess. So we go with some initial values. Okay. Next we change the values. Where we have gone? I think 2.5 to 0.9, something like this, right? So these are the changes in the two parameters. What a change? 2 here 0.7. Okay. Now this is a changes that we make in the parameters W comma B. Okay. Now so we have written in the vector form. So this is delta theta, this is theta. Okay. Now the resultant of these two is this curve, that is theta nu. Actually, is it okay? What exactly happened here? So when you add these two, okay, so the theta nu, the theta, this is the old theta. This is the new theta, which is a resultant. Now it has come in this direction. Is it okay? Actually, this is the actual theta, but the resultant of these two is this middle curve, middle line. Now it has come from this point, this region to this region. Okay, it has moved towards delta theta, in the direction of delta theta. Okay, anyway, so I don't want to get into the details of this because you might have studied all these things basically about the gradient descent algorithm. Now, so I have taken a small step in the direction of delta theta. Small step means, so here I have taken a small scalar that is called eta. Okay, so instead of taking entire delta theta, I am taking a small step in that direction. Okay, now this red line is a new resultant, that is theta nu now. Okay, so if you want clarity, let me draw here. So this is the theta. So I have taken a small portion. Okay, now this is the resultant, something like this. Is it okay? So what I have done here is, I did not take entire this theta, but this is small step in the direction of delta theta. Now this is the theta nu. Okay, so this is the movement. This is the movement. It has moved in the direction of delta theta only, but by a small amount, because I have taken a small step. This is a eta, which is a very small positive quantity. Positive quantity, but very small quantity. So it is scalar quantity. Now, so what is theta nu from this diagram? Theta nu equal to theta plus eta delta theta. Theta plus eta into delta theta. Okay. Now here we want to find out what is the right delta theta to use. So it comes from the Taylor series. Now I am not getting into all the mathematics because it is not required at this stage. Here for simplicity I am calling delta theta as u, some other variable u. Now what is the theta nu? Equal to theta plus, this is not in eta into u. Is it okay? Now, so we are taking this is a Taylor series. Okay, so we are finding we are expanding this function using the loss function, this variable using loss function, theta plus eta u. Okay, so if you expand this using a what series? Taylor series. What do you get? This is the expansion. Okay, so finally, since eta is very small, so we can neglect the square terms like eta square, eta cube, so on. So we are left with only parameters like, okay, so after expansion on deleting the small terms, now L of theta plus eta u is equal to, what do you got? L of theta plus eta u transpose del of L theta. Okay. So this has become L of theta plus u transpose del of L of theta. Okay. Now, so actually this is the L means loss. Is it okay? L means loss. So actually this is the old loss, old error. This is the new error. Okay. What do you want actually? You want to have a error less So we do so many iterations, right? Suppose you're doing first iteration. So compared to first, second iteration should be having less error. Obviously third should be even less. So on so on, right? Obviously, so this error should be less than this error. Then we are moving the right, then only we can say that we are moving in the right direction. Isn't it? Obviously, I want to have a error in the new error, otherwise new error, theta plus eta u minus the present error. So it should be less than 0. Is it okay? Do you agree with me? Is it okay? If the new loss is less than the previous loss. Okay? This is what we want. But from this diagram, from this equation, what is this? If you take this side, you are left with this quantity. Obviously, this means u transpose into del of L of theta should be a negative quantity. Please remember, u means a vector actually. What is u? Delta theta. Delta theta is, what is delta theta? It is a vector of two parameters. This is in the R2. This is also in the R2. Now, so this is nothing but a dot product. Okay, between what? So let me write here. If you remember properly, I told you. Suppose summation wi xi I equal to 1 to n. It is same as w transpose into x, which is same as w dot x. Now compare these two. W transpose x is same as w dot x. Here what we have? U transpose some other quantity, which means u into del of L of theta is two quantities. So I can say that u transpose into del of L of theta is same as a dot product between u dot del of L of theta. Is it okay? It's a dot product of these two vectors, u and del of L of theta. It is also vector. Okay. Now, so suppose if I say a dot b, what is this? Mod a into mod b into cos of theta or alpha, let me take here. Correct? What is cos of alpha? It's angle between a and b. Now can you tell me what is the range of this a dot b? It depends upon cos alpha, because mod a mod b is anyway the magnitudes of a and b. What is the magnitude of cos alpha? It is between -1 to +1. The minimum is -1, the maximum is +1. So which means, so the range of this a dot b is between minus of a dot, sorry, mod a mod b less than or equal to a dot b less than or equal to mod a into mod b. Is it okay? Because if cos alpha is -1, its value is minus of mod a into mod b. If it is 1, mod a into mod b. Suppose mod a into mod b is some m. So this a dot b lies between minus m less than equal to a dot b less than equal to m. This is the range of any dot product of two vectors. Is it okay? Now, so the dot product is minimum. What is the minimum value? Minus m. When it is minimum? When alpha is -1, when cos alpha is -1, which means alpha is 180 degrees. The maximum value is m when alpha is 0. The angle is 0. The angle is 180. What is m? M is the product of two mods, mod a into mod b. Okay. In the same way, so here also what happens here? So this is the angle between this. So here we want to have this quantity to be more negative. Please remember this. We want to have this quantity as negative. You want to have a more negative. If it is more negative, less the error. Is it okay? What is the most negative value of any dot product? Minus m. It happens if and only if the angle between the vectors is 180 degrees. What is minus m? What is m first of all? Okay. So here, but we are dealing with two vectors, u del of L of theta. Now, so I can say that suppose mod u and mod of L of del of theta is, let us take k. The mod of these two is k. The product of mod of these two is k. Is it okay, all of you? Let us go with the previous example, which means, so u dot del of L of theta lies between k and minus k. Okay, so its minimum value is minus k when beta equal to 180 degrees. What is beta? Is angle between these two. We want this to be negative. So if more the negative, less the error. What is the most negative value of this? Minus k. What is k? K is the product of these two mods. So simply the dot product is negative whenever the angle between them is 180 degrees. 180 degrees means moving in the opposite direction. So the direction, what is the rule now? The direction u that we intended to move it in should be at 180 degrees with respect to the gradient. In other words, move in direction opposite to the gradient. Okay. So the u should be in the opposite direction of the gradient. Otherwise, what is u? Delta of theta. So the delta of theta should be in the opposite direction of the gradient. Instead of u, you can say, don't get confused, this is delta, this is del. Okay. Delta of theta should be in the opposite direction of the gradient of the loss. That is the gradient descent algorithm. Okay. So delta of theta or theta. Now, so we have written something here. So theta of t plus 1 equal to theta of t minus, why minus? Because in the opposite direction, with a step eta of delta of L of theta t. This is the simple logic. Okay. Suppose t is a iteration number, first, second, so on, so on. Okay. Suppose we are at the past iteration number t. So in the next iteration, where we should be? We should be away from the gradient. We should move in the opposite direction of the gradient. Suppose at theta t minus, why minus? Away from the gradient. How much away? By a factor eta. It is called step. Actually, it is called learning parameter. So by this much amount, away from where? Away from what? Gradient. Gradient of loss function. Okay. So, but you know theta is a vector of two parameters w and b. So instead of writing theta, you can imply this to the two other parameters w and b. So obviously I can say that w of t plus 1 equal to w of t minus eta into delta of L of, okay, no need to write, so it simply becomes delta of w of t. So b of t plus 1 will be also same as bt minus eta delta b of t. Now these are actually not gradients, simply they become partial derivatives. Why? Because only one variable is there, no? Okay. Now this is the learning way. This is the best way of learning the parameters in each iteration. Okay. Now what is delta of wt? Obviously you go with this. So delta of L of w comma b by delta of w. This is at partial derivative with respect to b. We need to find out at specific points, very very important, at wt and bt. Now we have a more principled way of moving in the wt plane than our guesswork algorithm. So based on this algorithm, we will go to the a region where the error is very very minimum. This is the updation rule. This is how we update the parameters, moving in the opposite direction of the gradient of the variables. So why we move in the opposite direction? So this is a proof, simple proof, because you want to have a minimum error or minimum loss. For that you need to move in the opposite direction. So basically, so we should move in this direction, opposite direction. Okay. Now, so this is algorithm. So actually we should start with some initial values. Okay. So I am taking some 1000 iterations. Okay. So we run this program until we reach the convergences. Okay. Now this is how the updation rule works. Okay, this is simply the gradient descent algorithm which updates the parameters in the best possible way to get the minimum loss or error. Okay. Now, so here this is what we have taken, the sigmoid neuron. We have taken only one input for simplicity, and this is b, bias. So this is the sigmoid function. Suppose actually there are 2 points. We have taken these 2 points initially, x1 y1 x2 y2, something like that. Okay. So for simplicity, let us assume that there is only one point x comma y. Okay. So there is only one point, that is x comma y. So what is the loss function formula actually? Summation f of xi minus yi whole square. Okay. So actually 1 by 2 will be there. Summation I varies from 1 to n. Okay. But what I told you, we are taking only one point, that is x comma y. I am taking, there is only one point. Okay, initially I am taking only one point. So now my last function would be simply 1 by 2 f of x minus y whole square. Because the summation is not required because I equal to 1, that's it, n equal to 1. Okay, so what is a partial derivative with respect to w, all those things we have to do. So I want to find out del of w, which means it's a partial derivative, it is not the gradient exactly. Okay, now, so what do you get now? This is the function, loss function. Is it okay? Now, so what happens now? Something whole square, right? X square means what? Suppose if f of x equal to x square, what is the partial derivative? It is 2x. But here, so 1 by 2 into 2 into f of x minus y. But again we have to take the partial derivative of the variable f of x minus y. Is it okay? Please remember, what is f of x? It is a function of variables w and b. 1 by 1 plus e power minus w dot x plus b. Okay. So we are doing same thing here. So 1 by 2 cancels. This is into again. So here y will be a true value. Y is now independent of w. It's just a value, no? True value. It's only f of x now. Why? Because f of x is a function containing w and b. So this is the final. Okay. So after doing all these things, this is the final partial derivative of loss function with respect to w. What is that? F of x minus y. So finally, f of x minus y into, so otherwise I am writing wrong, just wait. F of x minus y into f of x into 1 minus f of x into x. Okay. So remember, this is only for one point, but actually there will be 2 points minimum. So if you take for 2 points, so this is for 2 points, it is for 2 points. This is delta w, delta b. Okay, this is simple mathematics, so nothing more than that. But what exactly happens is, if you implement the algorithm, now this is how the traversing will happen. So these are the values, this is the error. This is a principal way of moving or traversing around error surface to minimize the loss function. What has happened here? Initially we are in this red region. Okay, so we are moving, we have come to the dark blue region where the minimum is, the error is minimum. Okay, so this is the principal way of moving around the error function or error surface so that we get the minimum error or loss. Okay, now this is the gradient descent algorithm, that is the most optimum algorithm to minimize the loss, which means here, so we move in the opposite direction of the gradient. That's why it's called gradient descent. Okay, so this is about gradient descent algorithm. Right, so we stop here. Thank you.